to my lecture today. Of course, today is going to be the last lecture of the semester. Tomorrow, we're only going to focus on practice questions. Okay. I need the person online to confirm if you can hear me clearly. Is the person online hearing me clearly?
Yes.
Thank you so much. Now I'm going to share my slide now. I'm also going to need the person on the line to confirm if I see
We
my
can
lecture
see
slide.
the
Give me 1 second. It's still
whiteboard right
loading.
now and
Oh,
you, not your slide.
okay. I think I'm seeing. Well, can you see my lecture slide now?
Yes, we can both see your lecture slide and hear you and see your whiteboard.
Thank you so much for confirming that. Okay, so like I said, I want to welcome you to this lecture. This particular topic is a very interesting topic in time series in econometrics. Okay, and I need you to be more focused. Uh, Today we're going to be focusing on panel. We call it panel econometrics. So which is panel data versus time series data. Okay, so in the outline, I'm actually going to walk you through what do we mean by panel data, how do we analyze it, what are the techniques, statistical techniques involved in the analysis of panel data. Then I'm going to walk you through what I call the Lagrange multiplier test. What do we use, Osman test and case study. Then I'm going to make a conclusion. So all what I need from you is to focus on, what I'm going to be passing across today. I also need you to ask questions if necessary. Before now, I've walked you through regression type model or regression type analysis. I also walk you through time series, right? Okay, it's like what we want to do today is like it's a combination of the two. Does that make sense? Okay, but let me first give you the sense of what the data set we've worked on before look like and what the data set we want to work on now is going to look like. Take a look at this. Uh, I needed to first focus on, give me 1 second. Take a look at this. That's a time series data, right? That's a time series data, right? That is like looking at the price of a particular stock, okay, over days, right? December 1, December 2, and December 4. That's a time series data, okay? Okay, I wanted to take note of that. And of course, this time series data, I've walked you through method to, the method to use, like the autoregressive model, the moving average model, and so on like that, right? Okay, now let's look at the other one. Take a look at this guy. This is not a time series data. This is a cross-sectional data. Cross-sectional. What make it cross-sectional? Okay, the cross-sectional unit here is states in the United States, the Florida, okay, California, and New York. Take a look at that. Okay, now we have data set for one time point. Maybe this is for 2014 in a way. One time point, just one time point. Okay, but you have data set across sectional unit. Like the population of Florida in that year, the population of California, and the population of New York. This is in terms of a million. Then you know what the average income is. You know the percentage of people educated. And we're talking about that same year, and you know the amount of rainfall. Does that make sense? Now, this is a cross-sectional data. Does that make sense? And the first one is a time series data. Okay. Now, in the cross-sectional data, of course, in the cross-sectional data, you may want to look at the relationship. Of course, we can fit a regression type, right? Regression type, relationship, we've done that before. And of course, for the time series, of course, I've walked you through the models for time series. But you know what we want to do now? Let's now take a look at another interesting one. Oh my God, take a look at this. This is a panel data. What make it a panel data? Because I have collected data from a particular sectional unit more than one time. Okay, look at Florida. There's another Florida. Can you see that? Okay, the population of Florida in 2014, the population of Florida in 2015. Take a look at that. This is what we call a panel data. Okay, the panel data is a combination, situation where uh, you collected data, across cross-sectional units at multiple time. Okay, situation where a particular sectional unit can actually be repeated. Does that make sense? Now, this is what we mean by panel data. Any question on panel data? Okay. Now, another thing I want to walk you through is we have two types of panel data. Okay. Take a look at this. This is unbalanced one. What make it unbalanced? What make it unbalanced? In 2014, we only have data for Florida and California. Okay. But in 2015, we have data for Florida, for California, and for the New York. Okay, it means the New York data is missing in 2014. Does that make sense? That is an example of unbalanced panel data. Any question? Okay, let's go to the balance one. Want to go into the balance one? Take a look at this guy now. Okay. Oh my God. Take a look at this. We got information about Florida, California, New York in 2014. We also get information about them in 2015. That is an example of a balanced panel data. Any question? Okay, those of you online, can you still confirm again if you are still hearing me
Yes,
clearly?
we
Those of
can
you
hear
online,
and see.
thank you so much for that, for confirming that. Okay, now I just walk you through different type of panel data. Let me tell you this. The technique that we use in estimating parameter in balanced panel data is different from when we talk about the unbalanced. But you know what? In this, here I'm actually going to be focusing on balanced panel data. Does that make sense? Okay. Now I want to move away from this example now. I want to go to another example. It's very, very interesting. I need you to pay attention now. So let's look at this example. We collected um, you know, the wages and the education, the years of education of individuals at two different time points. Okay, this is individual number one. Okay, individual number one, we got information about the wages in 20, for year one and for year two. We also get information about the years of education for that same individual. Okay, when I talk about cross-sectional units, the cross-sectional unit could be countries, could be city, could be individuals, could be companies. Does that make sense? That's what we mean. Okay, now maybe we want to look at the effect of wages and the years of education, or sorry, maybe we want to look at the effect of years of education on the wages. Does that make sense? Now we want to look at the effect of education on wages, but this is a panel data. Okay. Of course, if it is not a panel data, if there's no situation where individuals are repeated or where there's no time component, we'll just go by way of linear regression that we've done before. We're going to use OLS. Okay. Now, but before I'm going to go into analysis of panel data, I think I need to first show you, what some stuff actually represent. Take a look at this from this data set now. Okay. You know, um, the way the wage is going to be, wage, and if the wage is Y, I'm actually going to have Y subscript I and T. Okay. I represent the cross-sectional component and T represent the time component. Does that make sense? Okay, I'm going to say that again. I represent the cross-sectional component and T represent the time component. Now, for instance, if I'm talking about the wage 1 subscript 2, okay, the way 1 subscript 2, it means I'm talking about the individual one at year 2. Does that make sense? And that is going to be 16.5. That's what I mean here. Does that make sense? You need to first get yourself familiar with that. Any question on that? Super easy, right? Okay. Now, wage 3-1 now. Okay, that's going to be 19. Wage 4-2 now. That's going to be 13. Is there anybody who has a question on this slide 7 before I move on? Go ahead. Exactly. Like I said, I represent the cross-sectional. It now depends on what you are using as a cross-sectional. Like here now, we're talking about individual. The cross-sectional could be individual, could be companies, could be countries, could be city. Does that make sense? Okay. Now, um, I'm going to clean my board now. Then I'm going to move to panel data regression. Okay. And I need you to pay attention now. Okay. This is a module, the panel data regression. We basically, the difference between this and the linear regression, there's not going to be a time component, right? There's no time component, right? In the linear regression, right? In the linear regression, it's just going to be yi. Some of you have seen the specification of multiple linear regression, whether multiple or simple linear regression. You're just going to have yi, xi, s1i, s2i, and the error I. There's not going to be, t component. Okay, but because the panel data has cross-sectional component represented as I and time component t, this is the way it's going to look like. And that was why I said we need to take into consideration now that we have variation across individuals and across time. So what makes panel data very interesting? Okay, we're basically going to use the idea of the variation across the cross-sectional units and the variation across time. Does that make sense? And you can see what the I and T represent. Any question? Okay, if there's no question, I'm going to go to the problem that we normally have. Okay, when we want to analyze panel data, the problem that we normally have when we want to analyze panel data is what we call omitted variable bias. Do you know what is going to lead to a omitted variable bias? For instance, I'm looking at the effect of years of education on the wages. Okay, and don't forget, uh, the information that I have, I have it across individuals, across time. Even there's a particular individual where we have the data for that individual for different time. Okay, there is possibility that individual will be correlating with the data. Like for instance, if I go back, let me come back here now. What I'm trying to say here, there's going to be correlation between the wages of this particular individual. Does that make sense? There's going to be correlation. Don't forget, if you want to use linear regression, there's an assumption of independence. That assumption is violated here because of the fact that the wages of this particular individual, number one, will be correlating. The wages on the year 2 will be depend on year 1. Does that make sense? Okay, that's a violation. Okay, and whenever there's a violation, okay, the violation is just going to tell you there's a relationship between what is observed and what is not observed. We don't expect relationship between them. Okay, so I'm going to say that again. There's going to be a relationship between what is observed and what is not observed. What is observed is actually, take a look at this. If I actually have this model for just cross-sectional, there's no problem. There's no time components. That's what we've been doing in regression, right? When there's no time component, when you only have cross-sectional that are not repeated. Does that make sense? In that situation, If I want to get the beta one, we want to get the beta one, right? Which is going to be the slope, right? We want to get this guy. Okay. The only condition under which beta one will not be biased is when this exists, when there's no correlation between predator and something that is not observed. Error is what we did not observe. Does that make sense? Error is any other variable that could have effect on the response that our model don't capture at the moment. Does that make sense? Okay, but we all know the moment a time component is involved, okay, that is not, there's going to be violation of that. Okay, and when there's a violation, that will lead us to have a problem that we call omitted variable bias. Why is it called omitted? It means a variable that is important. Where do we have it? We put it in the error. When a variable is important, it shouldn't be in the error. Does that make sense? Because when you hide something that is relevant in the error time, when you're telling the world, you're telling the world it is not important. And it is important. So that variable is what I call Z here. That variable is what I call Z. Okay. So which means for beta one to be unbiased, okay, and to be fantastic, we basically we want a situation where the correlation between you know the observed variable and the unobserved, that correlation, okay, should actually be equal to zero. Because when the correlation equal to zero, it means they don't have relationship. But in the case of a panel, it is not going to be equal to zero. That was why I said right here, I said we we know that so the beta one, so which means the takeaway is just going to be the beta one will be biased when the correlation between what is observed, like here, what do we observe? Years of education, and factor that we did not observe. If the correlation is not equal to zero, you know what I mean? It means they depend. When they depend, that will lead to bias. Does that make sense? That's what I mean. Okay. And this is also going to happen. Okay. So take a look at it. That's what they call omitted bias. Now, how do we now solve this problem of omitted bias? I'm actually going to show you now. Okay. Now, like I said, the panel regression model that we want to fit is this guy, where Y is going to be the wages of a particular cross-sectional unit at a particular time. And XIT is basically going to be the years of education of a particular cross-sectional unit, which is an individual at a particular time. And the error here is going to be EIT, which means there's also going to be a correlation for the error. And we don't want a situation where the error time will be correlated. Does that make sense? If error time are correlating with themselves, that's a violation of linear regression assumption. Okay, and that was why I said we now have observation for X and Y that varies by individual I and time period T. Now, this regression, as stated, will likely suffer from considerable omitted variable bias. You know why it's going to suffer? Because there's a relationship between what is observed. What do we observe? The years of education and variable that is not observed. Does that mean there could be other variable that determine wages, like experience, and so on, like that. Okay, so there's going to be a relationship between them, and the moment there's a relationship between them, the beta one cannot be trusted when you use a conventional regression approach. Does that make sense? Okay, now take a look at this. Because of that, in order for us, to actually control that, we're actually going to introduce, this is a model, right? Then we're going to introduce a time component, okay, into the model. We're introducing the time component into the model because we know there's X changes over time. You understand? What is X? That changes over time. The years of education changes over time. When you get into a job, maybe you actually you have a college, sorry, you have a high school diploma, and along the line, maybe you go to college, right? Which means your years of education to change over time. Does that make sense? Those of you online, can you still confirm again if you are still hearing me clearly? Those of you online.
Yes, we can hear and see
Thank
you.
you so much. Now I said we know that S changes over time. So omitting the passage of time will result in the omitted variable bias. And that is the reason why in our panel regression model, we basically going to incorporate the time component because we know that the variable of interest changes over time. Does that make sense? And that is what led me to including data high, data one, this very T. And if I want to go back into my data set I only have 2 years, right? If you take a look at this, year one, year two, year one, year two, only 2 years, right? Okay. So my time is going to be a dummy. Take a look at this. It's going to be dummy where I'm going to say, okay, I'm going to let TT to be one for year two for then 0 year one. Does that make sense? So that this year or the other year, I've walked it through dummy variable in this class. Okay. Now based on that dummy, okay, based on that dummy. So what we're basically gonna have now, okay. So based on the dummy, you're actually gonna have two different models, okay. One for when the year is for year one, for year one and for year two. Does that make sense? Okay. Now another thing we can do, the problem that we normally encounter is that the error is not going to behave like a white. Now the error is not going to behave well. Why is it that the error does not is not going to behave well? Because the error is correlating. We don't want that. Now I need you to take note of this. Take a look at this error. We can disaggregate the error into two. This error varies over time. That's what I mean, right? The error across individual varies over time. That was why you have EIT, right? Now we want to decompose the error into two, okay? Into, look at this, into alpha high, okay? The error is unobserved, and there are two types of unobserved. There's going to be one unobserved that doesn't vary over time. There's going to be another unobserved that vary over time. Now take a look at it for alpha I. Now alpha high, okay, is an unobservable, okay, that doesn't vary over time, only vary across the cross-sectional units. Why the VIT, okay, is the one that varies over time and also vary across the cross-sectional unit. Does that make sense to how we decompose the error in the panel regression model into two components? Okay, to alpha high, okay, the alpha high, the unobserved that varies across sectional unit, it doesn't vary over time. We also call it time invariant. We call alpha I time invariant, and we call the VIT time variance. Does that make sense now? Okay, why are we doing this? Okay, we are doing this because it will allow us to control for that kind of omitted variable bias, because the major issue with the panel regression model is the omitted variable bias. Does that make sense? And doing all this and decomposing the error component, that is actually unobserved into the variable, into the unobserved that didn't vary over time, and the one that vary over time, you're basically going to see what's going to happen now. Now, take a look at that. That's my definition for alpha I. Alpha I account for all omitted variable that vary across individuals, but they don't vary over time. That's why it's alpha I. You can see, does it have a time component? No. But take a look at the VIT that account for the omitted variable that vary over time and across individuals. Does that make sense? That makes sense, right? Okay. Now, we now know that that is what we have in our model. The error has been decomposed. I'm actually going to move. Okay. Now, take a look at this. The alpha high is what we actually call time invariant, unobservable, invariant. What do we mean by invariant? It doesn't change over time. Okay. And why the VIT is time variant, unobservables, Okay, does that make sense? So I'm just trying to give you the picture for that. Okay, now let us now go back into our model. What are we trying to do? We're trying to look at the effect of education, years of education on the wages. And don't forget, wages across cross-sectional unit and time, and the years of education across cross-sectional unit and time. I want it to make sense to all of you now. I told you the other time that EIT is decomposed, right? Now, let us see. The EIT is decomposed into unobserved that did not vary over time. They only vary across questionnaire units. Now, let us look at the unobserved. The unobserved, okay, that is time variant. I told you we're going to have time variant and time invariant. Does that make sense? Okay. Now, for the time variant, it's going to be experience. Okay. Why is experience time variant? Of course, experience varies over time. Your experience last year is not your experience today. It varies over time. What about your marital status? You could be single before and now married. That changes over time. Does that make sense? And that was not considered in the model. They are unobservables. Okay, but they are time variants, unobservables. What about the number of children? Varies over time. What about economic indicator like GDP growth? Varies over time. Okay, a time country could be in recession, a time country could be booming and so on like that. What are the time invariant now? Time invariant. When you say time invariant, we're talking about the the error component now. Okay, that's that doesn't vary over time, only vary across cross-sectional unit. Like ability don't vary over time. You can argue that with me. Okay, what about intelligence? Somebody say, oh, intelligence. What about going to school? You are just acquiring knowledge. Knowledge does not mean you are intelligent. Somebody that did not go to school could be more intelligent. Does that make sense? Okay, so knowledge could vary over time, but intelligence don't vary over time. Okay, then what about the city of residence? What about home country? Does that make sense? Just giving you the idea of that. Okay, this is a model that we actually want to use now, and don't forget our unobserved that we call error have been decomposed into two. Okay, those that are time invariant unobservable and time variant unobservables. Okay, now the alpha I in the which that is going to call individual fixed effects. Okay, the individual fixed effect is actually the time invariant unobservables. Does that make sense? The time invariant unobservables, the one ability, intelligence, city and stuff like that. Okay, now so take a look at that. Now, the next thing that I actually want to talk about now, take a look at this. Imagine you have included what is missing. There's not going to be any issue. What are those things that are likely to be missing initially in the panel model? Okay, initially we're looking at the effect of years of education on wage. Okay, and if we have included some unobservables that are time variants, what are the unobservable that are time variants? When marital status like married children, network. If we have included that, those are the ones that were missing initially that led to omitted variable bias. Does that make sense? Okay, because when you don't actually include them in the model, what are you assuming? You are where you hiding them. You are hiding them in the error time. Whatever you hide in the error time, what are you trying to tell the world? You're trying to say they are irrelevant. That's what it means. But what if they are relevant and you assume they are irrelevant? Then you've made an error, and that's what me to the omitted. That's what I'm trying to say. Right? I say if we include independent variable for all time variant factor and use a panel data model to control for alpha I, because the major issue there is the alpha I that we call individual characteristic, that I talk about, which is also time invariant factor. Then we will obtain an unbiased beta one. Don't forget what we're interested in. The primary variable of interest is to look at the effect of years of education on the wages. Does that make sense? Okay. Any question up to this moment? Any question? You're super good, right? Okay. Now, I'm going to now discuss different kind of panel models, and the essence of that is to control for alpha I. What is alpha I? That is individual characteristics that doesn't vary over time. Does that make sense? That's called time invariant unobservables. That is what we always want to control, because if you don't control that, your slope will be biased. And when it is biased, you're actually going to mislead. Okay. So now, after we have done that, you know what is going to happen? Then we'll be able to tell the world the correlation between the observed XIT, what is your SIT, years of education, and what is a VIT? The VIT is a time variant unobserved, right? Time variant unobserved, that I call the marital status, that I call the numbers of children that I included the other time. Okay, given what is the WIT? Okay, the WIT is that time variant unobservables. Okay, and the alpha I equal to zero. So which means if that equal to zero, what has happened? It means the correlation is equal to zero. If the correlation is equal to zero, then you expect your slope to be unbiased. That's what I mean. Okay, now what I want to do now, what are the method in panel data? What are the method that we use in estimating parameters in panel data? We have a pool OLS, first difference between estimation, fixed effect model, and random effect model. Okay, I'm going to first start with the pool OLS. You know, the pool OLS, just apply OLS to the data. What is going to happen? When you look at the data set, you know the OLS, the linear regression that we've been doing, you just applied it. What is going to happen to your beta one would be biased, because the OLS will ignore the time components. It's just like, take a look at this now. That's what I'm saying. I'm going to go back to the data set. Oh, like I said, this is going to take you back to the data set now. Okay, this is the data set. You know, if you want to apply OLS, you're just going to apply it on this guy, on this guy. That's what I mean. Where this guy is going to be Y, and this guy is going to be X. Does that make sense? What have you done? You've ignored the fact that it's a panel data. So if we use OLS, that linear regression, you're actually going to mislead. Why are we using linear regression here? Just to show the world that it's a bad fit. That's why we're using it. To justify using the other models other than the OLS. Does that make sense? Okay, so when you use that, it's going to be a bad fit. And why is it going to be a bad fit? There's going to be a violation of assumptions. Okay, all the assumptions, they're going to be violated. Of course, I've walked you through how, of course, that is obvious, because your observations are not independent. Because a particular cross-sectional unit was actually visited more than one time. Don't forget, independent assumption is very, very crucial in regression analysis. Okay, so now the next method is what we call the next method is false difference. You know, let me tell you this. I needed to take note of this. Whether false difference between estimation, fixed effect model, or random effect model, we are still using OLS. But before using OLS, you know what we've done? We clean the house. Does that make sense? But in the first one, pool OLS, we didn't clean the house. We just use OLS. So in the first difference between estimation, fixed effect, random effect, we're still going to use OLS. But before we use OLS, we first tidy it up. We clean the house. Does that make sense? Now, I'm going to show you how do we clean the house. When we're talking about first difference, please take notes. With first difference, how do we clean the house? This is our model, right? This is a parallel model. Don't forget, this is representing wage. Sorry, this is representing no, years of education. Okay, years of education, right? So this guy representing wage. Okay, that guy is representing wage. This is the time component. And don't forget, this guy, initially it was what? E, I, T. That we broke down. The EIT is unobservable, right? That we broke down into time invariant and time variant, right? Okay. Now, what we're going to do is, if we really want to tidy it up, if we want to clean the house, before we use OLS, we need to have a way to control for the time invariant, unobservable. What is the time invariant? Unobservable is alpha high. Controlling it is getting rid of it. Does that make sense? Controlling it is getting rid of it from the model. Okay? Getting rid of it. Now, this is what we're going to do by force difference. The other time I said, in the data set that we got 2 years, right? Okay? For t equal to 1 and for t equal to 0, by the time you plug in that in, you're going to have for the first module, you're going to have for the second module, then you're going to find the difference. Does that make sense? When you're going to find the difference, that's what we're doing here, finding the difference. At the end of the day, when you find the difference, what happened? What do you see? In the final module, there's no alpha high anymore. The alpha high is now eliminated. Of course, you remember in time series that I was using data differencing, right? That's what we're doing here. Okay. So, and that was why I said, notice that alpha I cancel out. We have to remove that heterogeneity effect across individuals. Okay, before we apply the OLS. And what we have now is we're now going to fit linear OLS regression on the final one. You are fitting regression now on the difference wage, on the difference years of education, and your error on the difference error. And we have an assumption that, okay, give me 1 second. The assumption here is that this guy and this guy, they will no longer be correlating. What do you see? Do you see any time component anymore? There's no time component anymore. Does that make sense? There's no any time component anymore. Okay. So, and that was what I was trying to talk about here. I said, notice this module now represents that of a cross-sectional, because there's only there's only cross-sectional component. There's no time component anymore. You've already eliminated that. Okay. Now, which means it only varies between individuals now, but does not vary across time. Does that make sense? Because the time differences have been removed. And when the time differences is removed, your beta one is going to behave well. Okay, your beta one will now be unbiased. But as long as the difference years of education and the difference of the error, okay, there's no correlation between them. Does that make sense? And what we cause the correlation is because of the time. When you collect data set over time, they will be correlating. You've removed that effect now. Does that make sense? Now, that is what we mean by force difference approach. Now, another approach is what we call the fixed effect. But before the fixed effect, there's another approach. Before I'm going to go to fixed effect, there's another approach that we call between estimation. Between estimation. Let me tell you what between estimation is going to do. I want to take you back to the data set. What between estimation is going to do is this. The force difference is better than the OLS. Okay. And between estimation is also a good one. But let me tell you what between estimation is going to do. Now, I need to focus on this data set now. What between estimation is going to do for individual, number one, between estimation is going to average this. Okay. For individual number two, is going to average that. Does that make sense? What has happened? When you average that, you're going to average not only this, you're also going to average for the, you're going to average that too. You're going to average that. You're going to average that. You're going to average that. How many data points are you going to have? 4. What has happened? It has eliminated time components. Does that make sense? So after doing this, they will now fit the OLS. That is between estimation. So between estimation, we remove the time component by averaging the variables involved. Then you're going to use OLS. That's great, but that doesn't solve the problem. Now, let me now take you to the first, the fixed effect. The fixed effect is the best. Okay, I'm gonna walk you to the fixed effect now. Now I'm gonna show you what the fixed effect does. You know what the fixed effect is gonna do? The fixed effect is gonna, this is the first, this is the model, right? Okay, the fixed effect is going to take the average, just like between, but take a look at this. Do you see y bar, x bar, v bar? That is the average. And you know what the fixed effect is going to do? It's going to subtract, which means it's more or less doing deviations. That's why subtracting this from this now will lead to this guy. Do you see that? That is what the fixed effect is going to do. Okay, so subtracting that, in the end, we're going to have, we're going to resolve to this, that will now give us this, so that I'm basically going to say, okay, what I'm trying to tell the world now is that this guy is this. You know what this guy is called? The mean variable. The mean means after subtracting the mean from each of the variable. Does that make sense? I subtracted the mean of the years of education from the respective data for years of education. I subtracted the mean of the wages from the respective value for the years, for the data of the wages. And what I have here is the mean years of education and the mean error. Take a look at that. This is how fixed effect work. And that was why I said the fixed effect regression is called the mean. The mean means you are removing mean from the variable. Okay, and of course the beta one will be unbiased provided the mean wage the mean years of education and the mean error, there's no correlation between them. That is by fixed effect. Now I want to walk you through a real life example. Now please pay attention, and I want to use a different data. Please pay attention. Here I want to feed the best model that show relationship between and its experience project undertaking and the numbers of years. In panel data, we're going to use a package called PLM that we call panel linear model. Panel linear model. This is the data set. Okay, I got the log salary, and this is employee ID, this is time, experience, project, education. Can you see that? Now, on this data set now, let us apply OLS. Do you see the code? Okay, pooling. When you indicate pooling, that is just using OLS. Okay, even though the experience is significant, numbers of project is not significant, years of education significant, but let's pay attention to the R square and the adjusted R square. Using OLS without cleaning up, without adjusting for heterogeneity across individual. Okay, the R square, the model is only go by 35 point something percent. Does that make sense? Now, by the time we apply between, you remember between? The between is going to take the average of the variable over time and actually apply OLS. Oh my God. Take a look at the R squared. The R squared actually gone up, and in the model, the experience is significant. The number of projects is not significant. The years of education is significant with the between. Okay. Now the next one, first difference is FD. Look at that, FD, first difference. Using the force difference now, what has happened? Oh my God. Force difference is a bad model. It's a very bad model. Look at the R squared and the adjusted R squared. That is extremely small, very close to zero. Force difference is not good at all for this data set. Does that make sense? Okay, now we now move to within. What do we call within? Within is fixed. That's another name for fixed effect model. Please take note. Within in the model, you're going to specify within. Oh my God. Take a look at that. The R square is 65%. I just said R square 56%. This is a very good model because the fixed model actually is, believe that there's a correlation between alpha high, okay, and the regressor. You believe that relationship exists between individual effects, okay, individual unobservable effect, individual, the one I call time invariant event. This uses alpha I and the regressor. What is the regressor here? Okay, the independent variables. Take a look at that. Okay, by the time we fit random, there's another model called random. Okay, in fact, in panel model, it is always between random and fixed. The random here is trying to say, okay, the correlation does not exist between, the time invariant unobservable and the regressor. But look at the R squared. The R square here is smaller compared to the fixed. So if you want to go by the R square, you're going to give it to the fixed, right? But you know what? We have a standard statistical procedure to decide between two models. If I want to know which one is better between the random effect and the OLS, I'm going to use Lagrange, the LM, okay, which is, I'm going to write PLM test pool. Where is the pool coming from? Of course, the pool actually coming from here. Do you see pool here? Okay. Now, uh, in the hand, you can see the p-value here. Because the non-hypothesis is going to favor OLS. Alternative is that it is random. And here now, you are rejecting the non-hypothesis. It means the random model is better than the OLS. Okay. What about considering between fixed and the pool? Between fixed effect model and the pool. Okay. Now, the pool, the non-hypothesis is pool. Alternative is the fix. And right now, what you see, the p-value is less than 0.05. You are rejecting the fact that, okay, pool is appropriate. So what is appropriate here is actually fixed. Okay. Now, how do we now decide between fixed effect and random effect? Like I said, in panel data analysis, these two are competing. In your non-hypothesis, it's going to be random effects. In the alternative, it's going to be fixed. You're actually going to use Osman test for this. There's a special test for comparing between fixed effect and the random effect. Does that make sense? Osman test, okay, which is going to be pH test into round, comma, dot. Then in the end, this is what you have. So here you're actually going to reject the non-hypothesis. The non-hypothesis is random. The alternative is fixed. Does that make sense? Now, what is the conclusion? Okay, panel data model is a method to estimate data, which is both time series and cross-sectional. Okay, it's very crucial to study the same cross-sectional unit, firm, country, industry over time, and it account for individual specific heterogeneity, which we call the alpha high. Okay, now uses in research. It's used in education research, like performance of different schools at different time. That's a panel. In clinical research, where you want to know the performance of a drug across races, that's a panel over time. What about in financial research? We've talked about stock today. Okay, if you want to talk about stock price for different firms. What about earth research? The earth status, okay, of different countries at different time. Any question? Oh my God, that's gonna be the end of. But let me tell you, in the final exam, number one question in the final exam will come from what we did today. You know why? Because I know it's going to be fresh in your memory. But you know what? You are not going to run any code. I'm going to provide you results. You're just going to interpret. Does that make sense? Why other questions will be the one, I don't know whether you saw what is it called? Um the practice question that I okay. So what we're gonna do tomorrow, what we're gonna do tomorrow is walking you through the final exam practice question, giving you more information. I think I sent you a message through the announcement section that you know when the final exam is going to be, and if you prefer either in person or online, and if there's anyone, if the time is conflicting with your schedule, I'm flexible, please send me a message. Okay, so this is going to be the end of the panel data that I walk you through today. Like I said, the probability that the panel data will be on the exam is 1, because number 1 in the final exam is going to be on panel data, but you are not going to run analysis at all. Okay, maybe you have a model and they say which one is better, using this test that I'm already going to give you. Does that make sense to everyone? Okay, so this is going to be the end of my lecture today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.
Thank you. See you tomorrow.
You're welcome.